Activation functions are used in machine learning for various purposes, and there are different shapes and sizes of these. We have things like Sigmoid, Tanh, Relu. While we don't actually need these functions to train a model, they are very useful and beneficial during the training process. They help us introduce a non-linearity, which enables a more generalized, the output will be more generalized, which provides higher accuracy for data that the model has yet to see. We also use it to control the output range. So during the feed-forward process, when we're activating neurons, we don't want to prevent any of the neurons from actually activating, which can occur if the numbers get way too small, or if the numbers are way too big, or if they hit 0, we have issues. We tend to run into problems. So these activation functions I kind of see as guardrails to help improve the quality of the size of the model. So if you've got a big matrix, you want to make sure that you spread the knowledge across all those floating point numbers. The outcome of not doing that is you potentially have explosions of some of the gradients, which can collapse some of the understanding and knowledge, create overfitting. General problems can occur. So say you did do a model without any activation functions, you have to be very careful about what kind of data you put into the model and the shape and size of that, because your model can very quickly, during the training process, it can lose large segments of its of the matrixy. Essentially, you can like corrupt part of the brain of the AI. And so with these activation functions, they help us and they protect us and they help keep things smooth and generalized. And in the case of something like a Relu, it allows the model to converge faster because it's a less compute intensive, right? So with Relu, it's just checking to see if the value is above 0. Computationally efficient versus doing a multiplication, which is expensive, or a division, which is the most expensive operation. There are various activation functions with machine learning. One of them is Softmax. Let's look at Softmax and what we can use it for. So with Softmax, you typically only will use this for an output layer on either the very end of the model as the last layer, or maybe a potential output for an embedding, which is a separate model that allows you to input high dimensionality and get out lower dimensionality. So Softmax, you won't necessarily use it for maybe training a model, especially in the middle of a model. You only would use a Sigmoid or Tanh or Relu. You would not use Softmax in the middle of a model. Really, it's good for providing just the ultimate answer output because it takes all the numbers in an array here, right? We've got all of our numbers here in an array. And then it's going to sum those numbers up together, and we're going to find the percentage of weight of the value that's associated with each of the inputs. So you can see like a 2, 1, like a 2, 1, and a dot 1 or 0.1. These numbers are going to convert to say, this is like 70%, this 20%, and 1%. The values and the output are always going to sum to 1 or 100%. So you can use these as a probability output, which isn't necessarily needed. You could just, depending on what you want to use the output of the model for, you might just want to find the maximum value as the output. So you don't need to run Softmax for that. You just find the max value. Or you might want to find the min value or the maximum absolute value. So you still don't need Softmax for that. If your outputs tend to be in the negative zone, then you might want to find the absolute value on all the numbers, right? So there's things to consider with Softmax. From an output comparison perspective, with the Softmax, you might want to look at the probabilities as a set. So this is where Softmax will shine, is when you need to look at multiple values, and you might want to have like a sort of the ordinal, which gives you like you could say the top 10, right? You could do something like that in a list. You can find the top 10 most probable, and then you can provide those as answers. That's a really good way to leverage a Softmax, for example. For the output layer in machine learning, we need these things called activation functions that help us guide our model into a learning scenario. Non-linear equations such as a sigmoid or tanh will allow our model to converge more quickly and without as many error probabilities. With sigmoid, you'll have a value is always going to be between 0 and 1 for every output data point. When you do a matrix multiplication with your input data, like maybe a string of characters, and you run that through the matrix, the layer parameters or the weights, you're going to get an output matrix. And a sigmoid would take each of those values, look at the number, and you'll get something that looks kind of like this. For example, we have an array of our output data, right? So this, after our matrix multiplication, we'll get an output array, and we'll get a number like this. Once we run it through Sigmoid, it's going to put it on this chart here. 0 is going to be 0.5. Large negative numbers are going to be closer to 0. Large positive numbers are going to be closer to 1. And this is useful because it will prevent dead neurons. For example, if any of these outputs would end up being 0, this would end up being 0.5, which helps the model generalize without losing opportunity within the matrix. Because if you had a bunch of zeros as you're feed forwarding, you're going to be deactivating a large portion of that matrix, like a percentage. Typically, you don't want that. I can see scenarios where you might, however, you're going to be reducing, most of the time you're going to be reducing the overall effectiveness of the number of weights and parameters that you have in the model. So this is why Sigmoid or any other activation function is really valuable. Sigmoid is also often used as an output activator if you are doing a classification within, say, like maybe an image, you're looking for a dog or a cat. So the image has a probability of being one or the other. However, you might have additional attributes that you are looking for with that classification model. You might be looking for, like, is it nighttime or daytime? That might be an interesting addition that you want to train the model on. And so you could have those as well, in addition to whether it's a cat or dog, is it day or night? And then in that case, you wouldn't want to softmax it because now you have a mixed output. And you could totally do this because there are many applications that will gain advantage by doing this. So you would use something like a sigmoid function that would help provide values between 0 and 1, which will generally give it a probability of how close it is. And then you can use this as a backpropagation technique as well, so that way the model can converge. So it's one of the great things about Sigmoid, which I really like, is because it's multi-purpose. And the same goes for Tanh. However, with Tanh, you're still going to get those negative numbers, and we'll check out Tanh as well. So Sigmoid is good for feed-forward activations on a layer-per-layer basis. There is a computation cost because there's division involved, and division is, one of the most, if not the most expensive computation. You can also use Sigmoid as the final output layer, so that way your numbers are represented in between a 0 and 1. And you might put a threshold in there for making a decision, like say maybe if the model has a 60% chance of likelihood that this is saying it's a nighttime, then you might say if it's above 0.6, then you would consider it nighttime. Something like that. Tanh is another common activation function that we use in machine learning. For example, in a feed-forward neural network, I tend to like to put Tanh in a couple of specific spots because it performs really well. It's usually as an input during vectorization. I can use it there. I can use it on the first few layers, and I tend to get pretty darn good results. There is a drawback that it is one of the more expensive activation functions, so your model will train a little bit more slowly. However, I tend to find better quality answers because it's got a nice range of opportunity between -1 and +1. And as you can see, if your output data is, let's take a look at the output data as an example. Say we've got a -1 as the output from either an embedding or vectorization, or as one of the layer outputs. We're going to see that it maintains that negative symbol, but it also keeps everything in between -1 and +1. Throughout various efforts of training various models, I have found that Tanh does provide my favorite of the results. It seems to do a really good job at keeping within the scope of keeping a gradient nice and smooth, and it has the ability to see like two sides of the picture, because you might, as you're doing back propagation, you might need to be able to demote some numbers as well. You could, in any case, you could do that from with Sigmoid. I just tend to see a little bit more range of accuracy using Tanh, and my models tend to perform. It is one of the more expensive computations for an activation, and because of this, especially when we're training larger models or models that we're processing images for with image data, you might want something a little more performance so that you don't have to spend so much money on training the model. So you're going to trade off with like nice accuracy and pretty good outcomes for every single run. Or on the other side, there's another activation function that we could check out called Relu. Relu is an activation function that we use in machine learning models. The cool part about it is it's the most efficient. It is absolutely the most efficient activation function that we have available to us at our fingertips. And it is so efficient because it is a simple flow control based on the number. It basically checks, is this number below 0? If it's below 0, I'm going to set the value to 0. If it's above 0, I'm going to keep the value as is. What this does is it helps maintain a somewhat non-linearity, and it also has an advantage over the other activation functions like Tanh and Sigmoid, because with those two other functions, they require division and multiplication during the forward propagation and back propagation. That means more compute is required. However, with Relu, you're just doing a simple if statement. If this value is greater than 0, then keep the value. If it's below 0, we're just going to set the value to 0. There's a trade-off though, because now we're saving values as 0, we will lose accuracy over time. We'll be deactivating neurons in entire rows of your matrix, which becomes problematic and generally wasteful. So you might need to increase the number of parameters. However, this still could work out well in your favor depending on the model and your desired, like, what are you targeting? Like, are you doing classification? Maybe you're building a transformer, or like generative, like the new, generative AI. Relu is really popular because of how efficient it is. It is the most efficient. Because of the drawbacks though of the loss of accuracy and the need to have larger models, which, I guess is kind of like counterintuitive, because if you have more data in your model, then the Relu, its lossiness is less problematic, but then you still have to do a lot of work. But even though, since the Relu is so efficient, you can have larger models move forward more quickly and train the model more quickly. So that's why it's so popular. However, you might still want to use Relu for a smaller model, but you don't want to necessarily have to throw away large sections of all your weights and parameters during training and inference. So there's a couple of other options, such as leaky Relu and randomized leaky, the randomized leaky Relu, which is the same thing as leaky Relu with just some randomization that occurs in there. So if we take a look at some of the math here in Python, it's simply regular Relu is checking to see if x is greater than 0, return x, otherwise return 0. So you can see here that we have this array, which is our input array. I'm going to rearrange that for us so we can see it a little bit better. So you start with this array. Negative number is always going to be 0. And if it's above 0, it's just going to return the number that it was before. If it's below 0, it's going to be 0. It's above 0, so return 0. So you can see that with a Relu, it's really simple. It's really simple. It's just eliminating negative numbers. That's really all it's doing. That's kind of interesting. So if we take a look at the leaky Relu, we can see here that we start with the array that we had before. However, now we're no longer eliminating zeros. We're just making the numbers smaller. If they're below 0, we're just going to make them smaller. So in this case, alpha, it appears to be, so you can kind of change this number around. Alpha is just sort of like an epsilon or a really low number. You can check to see if it's above 0, return x as normal, right? Like we saw in the standard Relu. But if it's below 0, instead of just returning 0 directly, we're going to do a multiplication on x, and that's just going to make the number smaller. So this helps preserve your matrix and the feed forward aspect, so that way you don't deactivate any of the rows in your matrix at the cost of extra compute, because now you're doing a multiplication, which is, like the second most expensive computational operation next to division. It's still more efficient because you're only sometimes doing multiplication, because you're checking to see if it's above 0. So you're still in a more efficient approach. So you still could prefer Relu in this case because it's going to give you a better of both worlds. You're still going to get mostly efficient, and then you're going to be able to cover some of the edge cases where you might be throwing away data with zeros, which would deactivate neurons. So there's a win here. There's still a win. And you can go a step further with a randomized leaky Relu. You might want to store this random number and keep it as a constant, or you can do it like this, which is going to give you some interesting training outcomes, because it's going to randomly adjust every single neuron based on and it's going to make things very fuzzy. You can adjust this as needed. Maybe we'll add some extra zeros in there, but you might want to randomize leaky Relu if you want to sort of reduce on overfitting. It is going to add an extra computation step, but it is a neat way to help improve the accuracy of your model. If you have a lot of data, but then your test data, you want to test it to see how accurate it is, you might get a better outcome if you use a randomized leaky Relu. There are more activation functions in machine learning. These are the most popular that we've checked out, which is Tanh, Sigmoid, Relu, and Softmax. Softmax is mostly just for output layers.